Hi everyone. My name is Chunlong Huang.
And Qasem Izadi dast kardی.
Here we're going to present our semester project. So just give a quick overview of the physical problem that we are trying to solve here. So in this project, we perform a thermal analysis to a section of the wind turbine blade that embedded with heaters. The heater here is really used for preventing the turbine blade from freezing or getting too hot. Wind turbines are installed in many different places in the world. So in some of the location, the temperature can get to really extremely cold, which can go even below -10°C, which is like in Massachusetts. So the freezing temperature can lead to a frozen wind turbine blade. So the wind turbine cannot generate electricity because of that, or even lead to a costly repair. Therefore, we want to analyze whether the heater is sufficient to keep the exterior surface, in this case, which is top and the left boundary, from freezing. And also, we also don't want the exterior surface to be too hot. So the heater we're using here is about 200,000 watt per meter square here. So and the top and the left boundary, we have they are exposed to the ambient temperature, which is -10°C here. And the bottom boundary, we have a fixed temperature at 0°C. At the bottom here, is the 2D equation we are trying to solve we use to solve this problem. So it's really the heat transfer Poisson equation. We also simplify this 3D problem into the 2D problem. How we simplify it will be demonstrated in the later slides. Yeah. In this slide, I just want to give an overview of the way we approach the problem. So we first analyze the physical problem and make necessary assumption to simplify the problem. And then we did the console solution first. We performed the console analysis to get the benchmark solution so we can compare with our numerical solution. And then we start off, and then we finally go into the finite difference method. After the finite difference method, then we go with the finite volume method. Then we compare the answer and the solution, or the solution from both methods, with the solution from the console solution. And we also performs the error analysis to compare the error or the deviation in between the methods.
First, we are going to talk about the domain. An actual bullet is not a perfect rectangle, but we picked a small domain sizes that every block can be considered as a rectangle. If we compare the actual size of the bullet and its cross sections, that would be up to 5 meters, and compared with our domain that we picked at 20 centimeters. So our assumption that every domain is a rectangle is sufficiently accurate. And next thing about the domain is that we have two domain types. The first and last block is means these two blocks, this one and this one, the last one, is imposed to the ambient temperature from two sides, but the middle blocks are just imposed to ambient temperature from the top side. So for this project, we picked a critical block that is faced to ambient temperature from two sides. And calculating for the middle block is just changing the right or left boundary condition. Here we can see the discretization geometry for the finite difference method. And the next slide is discretized geometry for finite volume method. And next slide is the discretizing the governing equation for finite difference method. Here is the general equation, and this side here is the right hand side. Next slide is governing equation discretized for a finite volume method. General equation and an x side, y side, and after simplifying and manipulating, this equation goes to the metrics that we use for our code. And talking a little bit about the right hand side, we picked our heat source as 200,000 watt per square meter, and this amount, this heat is the minimum heat we can pick. Basically, is optimized peak, and also with picking up the a small enough delta x and delta y, we could cover up the curve of the wire inside the blade. And so basically, our domain is 20 centimeters, and every mesh, every segment is around 1.47 millimeters long.
So in this slide, I'm talking. We're showing the boundary condition we apply to the to our numerical method, finite difference method, and the finite volume methods. So for the bottom boundary, we have a fixed boundary condition, which is the Dirichlet boundary condition with temperature at 0 Celsius. So it's kind of the same for both finite difference method and finite volume method. The discretized form of the left-hand side is slightly different, but overall it's pretty similar. For the y boundary side, we have a Newman boundary condition, which does not have a heat transfer in between. At that boundary, there's no heat transfer there. So just because we have that's kind of the symmetric section, there's a symmetric section right next to it. So we perform a backward difference and to generate the equation for the matrix, A matrix, and similarly for the finite difference method. And similarly, we also do the backward difference for the finite volume method to come up with this discretized form of the equation for the right boundary. And for the top and the left boundary, is really the convection comes into play. So because they both expose to the cold air, so the convection equation is used for in this case for the as the source term, and then we perform the backward difference approach to get the discretized form for the matrix C side, and then we manipulate move all the unknown to the left hand side and put all the unknowns to the right hand side. That's why we come up with the known value, or here shown on the right hand side. Similarly for the left boundary as well, it's just like the left boundary use the convection coefficient, or for the left side, and the top use the top side. And for the finite volume method, the way we get this discretized form of the equation is also through a backward difference method as well. So that's why they look pretty similar in this case. So after all, we we did our code, and then we come up with this solution. So here, these are the plots for the overall temperature distribution. So three plots looks really similar. So it might be difficult to tell whether they are the same or different from comparing to these three plots. But you can really see there's no location within the domain are lower than the 0 temperatures. And the center of the domain is the hottest point, which is the heater, where the heater is embedded. So the area of interest are the top boundary and the lab boundary, because those are the area that exposed to the cold air. So in this slide, we plot all the solution for we plot the solution for all three methods onto one single plot for the top boundary. So as you can see here, the orange line here is really the console solution, and the other two lines are either the finite difference method or the finite volume methods. So they get really close to the console solution with a small deviation, and again, none of the point on the top boundary get below 0, and so from comparing to the plot, so we can say the solver we come up with pretty working properly in this case. And similarly for the lab boundary, we also plot the lab boundary temperature for three methods on the same plot, and we also see a small deviation here as well, but the deviation is also considered to be small. I think it's within like a 0.2 Celsius. So this also tells us that the solvers are working properly as well. And none of the point here really goes below 0 as well. So it tells the heater is working properly as well. So in this slide, we also did some error comparison. So as you can see on this slide, on the top boundary error, we see that the finite difference, we get a little bit more error as compared to the finite volume method, and the same for the lab boundary as well. So this might suggest that the finite volume method seems to have a more consistent and smaller error throughout the top and the lab boundaries. So, however, I think the small deviation from the finite difference method is really because of the limitation of the method itself. Due to the heater we have, it really has a curved surface, and the finite difference method is not really the best method here to solve the problem with the curved surface. And for the finite volume method, if we want to minimize the error, so we can probably use a irregular shape volume around the wire. That way will be we should be able to minimize the error.
The application of this approach can be seen widely in industry. For example, steam or electric tracing is a very common method for keeping the temperature of equipment or piping lines in an allowable range. And finally, for conclusion, the calculated heat source is enough to prevent the blade from freezing, and this amount is the optimized amount. And as we've seen, the finite difference method and finite volume method have almost the same result as the result of commercial software, the COM solvent that we used. And between this method, the finite volume method has more accuracy. Thank you for watching. Now you just start to.